Hello, George Romanic here. Today we are going to talk about intensive and extensive properties of materials and systems, and we will also later in the video define specific properties of a system. There is a couple of ways to define intensive and extensive properties. One way is to say that intensive properties of a material do not depend on the amount of material. They are mass independent. Logically, then extensive properties do depend on the amount and mass of material. Another way to define intensive properties is to say that they are defined in every point in space in that material that we are examining. So they can be defined in terms of imaginary point that doesn't have some finite geometric size. Extensive properties, on the other hand, require area or volume or something like that to be defined. Now, I would like to have a glass of whiskey and further discuss these intensive and extensive properties of the system. One of the intensive properties of the system that doesn't depend on the amount of material is color. You see, this whiskey has brown, yellowish color, and if I drink a little bit, it still has the same color. Therefore, I reduced the amount of whiskey, but the color stayed the same, which means color is intensive property of the system. Now, color of a substance is related to refractive index, and therefore we can conclude that refractive index is also intensive property of the system. Temperature is intensive property of the system. Temperature of the whiskey, because I didn't put any ice, this is room temperature, 23 degrees Celsius. I drink a little bit more. It is still 23 degrees Celsius. If I add more whiskey, it will be 23 degrees Celsius. So the amount of whiskey doesn't alter temperature of the whiskey. Another example of a property that doesn't depend on the amount of substance is hardness. Now it's difficult to define that in terms of whiskey, so I brought here two pieces of wood. And I used these pieces of wood in my video on bullet penetration. These are two same materials, two same types of wood. They have the same hardness, despite the fact that this one is larger than this one. In fact, if I break this one in half, all these three pieces, different sizes, they have the same hardness. So changing size doesn't change the hardness. Next thing that doesn't depend on the size and is intensive property is surface tension on a surface of a fluid. Let's examine that. Here I have two metal needles, identical, and two containers half filled with water. This one is 2 times larger than this one. I claim that the surface tension of the water is independent on the amount of water in these two containers. To test that, I will place these needles on the surface of the water. This one works quite well. Let's see this one. Also works quite well. Now, if these needles synced, you would say, Professor Romanic, experiment failed. But I will quote great physics professor Julius Sumner Miller, who said, experiment never fails. It's the person that fails to satisfy the requirement of the nature, but not the nature or physics or the experiments. They always succeed. Interesting experiment, right? Now, another intensive property of substance is density. And that's also logical, because when you tell someone that density of water, for example, is 1000 kilograms per cubic meter, you don't say it's that density given this amount of water. It's regardless what is the size of the water of the container, that's the density of water. The same is for density of air. Density of air in this room is about 1.2 kilograms per cubic meter, regardless of the size of this room. Another intensive property of a system is pressure. But I will go back to pressure later because it's one of the tricky intensive properties of the system. So now let's check some extensive properties of the system, because it seems everything is intensive, but it's not. The most obvious extensive property of the system is mass. Mass of the substance, material, system depends on the size of that material. Mass of whiskey in this glass is not the same if I add whiskey or I drink a little bit more. I just decreased the mass of the whiskey, but density of the whiskey, temperature of the whiskey, all these stay unchanged. Therefore, they are intensive. Mass is extensive. Another extensive property of materials is volume. If I increase the size of materials, volume changes. And the best example is, again, these 3 pieces of wood, or these 2 pieces of wood. Same materials, volumes, clearly different. Area is also extensive property of the system. Energy is extensive property of the system. Because if I have a toy car like this, and I hit you with toy car, nothing crazy will happen. But if you go out and you get hit by real car, bad things can happen, because kinetic energy is extensive property of the system. The same is with internal energy of the system. Internal energy of water in ocean is much, much higher than internal energy of water in these 2 containers that I have here. Entropy is another extensive property of the system. Entropy is very interesting variable and physical concept. I will talk more about entropy in future when I start talking about thermodynamics. But for now, you can think of entropy as the number of ways you can rearrange components of a system. So of course, if you have a larger system, there is more ways you can rearrange, permute these components. And therefore, entropy is size dependent. And I could go on and on and on and on. But I would now like to go back and talk a little bit about pressure. Pressure is intensive property of the system. Now it's sometimes a little bit difficult to understand, because you think, well, if I have a tire, it is under certain pressure, and I add material, I increase pressure. Shouldn't then that be extensive property of the material? The answer is no, because you are keeping volume the same. So when you are changing size, or to be more precise, when you are changing mass, you have to change accordingly volume in order for the thought experiment to have meaning. To further demonstrate that pressure is intensive property of the system, let's look at the following 2 thought experiments. The first thought experiment is the following. Imagine you have 1 liter of water floating in the outer space between galaxies, far away from any influence of any external force. Because this is thought experiment, we can imagine that water is liquid. In reality, it would be frozen. Outer space is very cold. But let's imagine it's liquid. 1 liter of water, it would be a sphere, and it's floating between galaxies. Now, from distance, another liter of water approaches. It has the same pressure and temperature as the original liter of water that is sitting there. When they merge, the temperature and pressure of these 2 liters of water will be the same as pressure and temperature in the individual liters before merging. However, mass will be doubled and volume will be doubled. Therefore, pressure and temperature and density are intensive and volume and mass are extensive. Another way to say that pressure is intensive property of the system, which is more like a way around, would be to say that pressure is force per area, and both force and area are extensive properties of the system, and when we make division between two extensive properties of the system, we get intensive property of the system. The other thought experiment with pressure is the following. Let's say you have a large living room and you decide one day to redecorate that space and split that room in half. At the same time, imagine that there is a lazy cousin sitting on the bed and he doesn't want to help you while you are putting a barrier between to split the living room in two. Once you finish that redecoration, living room has 2 smaller rooms, so the volume is split in 2. Mass of air in both of these smaller rooms are half of the mass of air in original living room, but your cousin is alive on the bed and it's not suffocating because pressure stayed unchanged. When you split living room in 2, you didn't decrease pressure in the 2 rooms that you created. I hope this was clear enough. The last concept I would like to talk about is the concept of specific property of the matter. Specific property is any extensive property divided by the mass, and it is intensive property. Okay? Specific volume that we talked about in my video on pressure as vertical coordinate. Specific volume is volume, which is extensive property, divided by mass, which is also extensive property, and we get specific volume, which is intensive property. Heat capacity of an object is extensive property. It's not the same to heat 1 glass of whiskey and to heat up a huge container of whiskey. So it takes more energy to heat larger materials. That's why heat capacity is extensive property. But specific heat capacity is intensive, because specific heat capacity is heat capacity divided by mass, or it is heat capacity per unit mass, we would say. You can see now that specific quantities or specific properties are built when we take extensive property and we divide it by mass, and we always get intensive property. At the end, some of you might be saying, this is all nice, but who cares? Why do we even need this classification? There are 2 answers to that question. One is more scientific and formal, and the second one is more practical. Let's go first with the formal. If you are dealing in your problem with objects of finite sizes and you know everything about that material, then indeed you can use extensive properties of that material to carry out your analysis. An example, you are a structural engineer that needs to calculate a load exerted by some box on a building. Just give me mass of that box, size of that box, and I'll calculate and continue with my life. Another example where it's easier to use extensive properties of materials is from my video on the broken physics in Wonder Woman 1984. In that video, you will remember we had a situation of a collision between Wonder Woman and 2 kids. And we used masses of these 3 physical objects to estimate the impact force, because that was the easiest way to solve that problem. Now imagine if I wanted to be fancy and convoluted and I said, okay, specific weight of a female body is such and such, and Wonder Woman has these properties, and therefore impact force is such and such. That would be unnecessarily complicated and maybe even strange. And therefore we just use masses and we solve problem easily. However, in the case of fluids, situation gets more complicated. Because fluids operate in the realm of continuum. What does that mean? The very first video on this channel was a video on the atmosphere as a continuum, because I think that's one of the most important principles. The principle of continuum says the following. If you have a fluid, such as fluid in this air, you can divide that fluid indefinitely, you will always have fluid. There are no atoms, molecules, or some elements of finite size that form that continuum. You can also add more continuum indefinitely. So in these cases, you see it's difficult to specify mass. Moreover, fluids are flowing around and mixing. So if you say, okay, this is my mass, well, if there is wind, that mass goes somewhere far away, or it mixes and so on. So it's very difficult to specify mass or any other extensive property of a fluid. Therefore, we like to use intensive properties of fluids because they are size and mass independent. You will remember in my video on Navier-Stokes equations, I said in atmospheric sciences and fluid dynamics, we don't write second Newton's law as force is equal to mass times acceleration. Instead, we say force per mass is acceleration. And now, after watching this video, hopefully it clicks. Because force per mass is intensive property. Any extensive property, in this case force, divided by mass, as I just said, is specific property, and specific property is intensive property. Moreover, in Navier-Stokes equations, you will remember we have pressure gradient force, viscous forces, Coriolis force, centrifugal force. When I derived these forces, we always derived force per mass, per unit mass, because that is intensive property of air, of fluid. If I didn't do that, then I would always have to tell you, okay, I derived this expression, but it holds for this amount of air, this mass of air. And that would be difficult. Like, what does it mean? How do you apply it? Is it amount of air above Montreal? Amount of air above North America, whole atmosphere, and so on. Therefore, we like to use intensive properties of the fluid. That was a long answer to give you formal reason why we need this separation between intensive and extensive properties. Practical answer is the following, and it's similar to my reasoning in the video on non-Newtonian fluids. Namely, over there, I said after watching that video, when you go to a bar, you don't need to ask for ketchup, mayo, mustard. You can just tell them, can you bring me all non-Newtonian fluids that you have? Along those lines, you can do the same with the intensive and extensive properties of the material, as following. Tomorrow you go to a bar, and the waitress comes and says, oh, we have wide range of beers. The question that you should ask is the following. Can you please give me the list of beers in terms of their extensive properties and list of beers in terms of their intensive properties? And she should tell you, okay, in terms of extensive properties, we have small, medium, and large beer. In terms of intensive properties, we have dark beer, light beer, red ale, sour beer, and so on. Now you know. Test that. Go tomorrow and try to do that, and let me know in the comment section below how it went. Well, not tomorrow, but in the next video, we will use these concepts to develop one of the greatest theorems in fluid dynamics, Reynolds transport theorem, the backbone of fluid dynamics. Until then, goodbye.